this project, we were tasked with building a small glider that could travel at least 20 feet forward. Success was regarded as the glider fitting in a 16 by 16 inch square and a 20-foot or longer throw during the tournament. The glider needed to be built primarily of balsa wood and had to remain intact. It also needed wings and had to be built using easily accessible materials. However, before I could throw a glider, I had to design one. The first thing I considered was wing shape. I had to decide between an elliptical shaped wing, a rectangular wing, and a tapered wing. Elliptical would have been very difficult to manufacture consistently, so I decided against that one first. The rectangular would have been easiest to make, but the aspect ratio would have been lowest. Finally, the taper seemed relatively easy to manufacture, and it kept the aspect ratio high. As such, I decided on a tapered wing shape. The next thing I had to decide was the dihedral. I had to decide between a steeper dihedral, a shallow one, or no dihedral at all. After doing some research, I decided that I wanted to include a dihedral because it would add some stability. Not adding a dihedral would have maximized the lift, but I decided that for this set of requirements, lateral stability was important so that it would travel straight. Originally, I wanted to cut notches in my fuselage and place the wings in an angle to provide shallow dihedrals, but that proved incredibly difficult to make. Steeper dihedrals proved the best because they required less precision and provided the most lateral stability. However, they did sacrifice the most lift. Lastly, I had to consider wing placement. I considered putting the wings halfway up the fuselage in notches cut for them, on the fuselage but right behind the nose, and on the fuselage around 1.5 inches from the nose. Putting the wings in notches would have allowed me to control the dihedrals a little better and provided more space on the fuselage for weight distribution. However, that was very difficult to make. Putting the wings right behind the nose would have shifted the center of gravity further forward, increasing the static margin, but it made it harder to put additional weight on the glider. Adding some distance between the nose and the wing let me add weight to the glider more effectively because I could shift the center of gravity more with weight close to the nose. I believe the most effective alternative would have been shallow dihedrals, the wings placed in notches on the fuselage, and elliptical wings. Dihedrals are important for lateral stability, so even if I had to change, I would go with shallow dihedrals to increase lift and preserve some stability. Putting the wings in the fuselage would make them more durable, as it would be less likely for the glue to fail. It also would allow me to make the angle of the dihedrals much more exact. Elliptical wings would have a larger aspect ratio than rectangular wings, although they are harder to manufacture. Initially, I went with a wingspan that was a little less than 16 inches across. However, I made the length of the fuselage much smaller, around 8 inches, in order to limit weight. This proved to be an unstable configuration because the static margin wasn't large enough, so in my second iteration, I made the fuselage 15.5 inches. This increased the static margin and made the glider much more stable. My initial set of design choices was a short glider with a small vertical and horizontal tail. It had tapered wings with a long wingspan and a high aspect ratio. It also had a nose cone. This glider was not very stable. It tended to veer right even after weight was added to stabilize it. This was a true glider, using nothing but lift generated by the wings with no remote control. It was built primarily of balsa wood, and the other materials were easily accessible. This glider was less than 16 inches by 16 inches, so it fulfilled the size requirement, but it only occasionally went 20 feet, meaning that requirement was not adequately met. In order to improve the stability and have it fly further, I decided to increase the length of the fuselage and add a larger vertical tail. I also decided to sand down the edges of the fuselage at the front of the glider so that it would fit snugly with the nose cone, reducing drag. After balancing the new glider, my center of gravity was located a little behind the quarter core, even with the trailing edge of the wing. My glider weighed 27 grams, had a wingspan of around 0.4 meters, and a wing planform area of 0.0152. The last thing I needed to find the lift coefficient was the average velocity. I conducted 3 trials and found that my glider moved at an average velocity of 3.39 meters per second. I estimated my lift coefficient using this equation. The lift coefficient was around 0.252. After finding my lift coefficient, I could find the coefficient of induced drag. I found that using this equation. That gave me a value of 0.00214. The drag coefficient can be estimated as 2 times the induced drag coefficient, so my estimated drag coefficient was 0.00428. These design iterations made my glider much more stable, so it flew much further. This design fit the requirements well. It was just under 16 by 16 inches and would consistently fly over 20 feet. It was a true glider with no propulsion and a glider body, including wings. It was also made almost entirely out of balsa wood, with the other materials being easily accessible. This project forced us to consider all parts of aircraft design as a whole and consider the trade-offs between different characteristics of an aircraft, like the trade-offs between stability and lift for dihedrals. This helped tie everything together we learned in the course and was a fun way to end the semester. If I were to continue to try to improve my design, I would probably increase the dihedral angle and try to make the glider more durable. It broke very easily, causing problems during testing and on flight day. Finally, here are my references.